1/3 of all food gets wasted, 1.3 billion tons every year. But what if that trash could be treasure? In this video, we'll show you how modern factories turn food waste into fuel, fabric, and more. Did you know that restaurants in the US throw away enough food each day to fill the Rose Bowl Stadium? That's just one small piece of our global waste crisis. Every year, approximately 1/3 of all food produced worldwide, about 1.3 billion tons, ends up wasted. That's equivalent to more than 80% of Russia's annual GDP literally thrown into the trash. Food waste occurs at every stage of the supply chain. On farms, perfectly edible produce is rejected due to rigid cosmetic standards. These ugly fruits and vegetables never make it to market, despite being nutritionally identical to their perfect counterparts. Processing facilities generate trimmings, peels, and byproducts, while restaurants and homes discard plate scraps and expired items. Think of food waste like leaving your car running 24/7 in your driveway. Resources continuously consumed with no benefit. When we throw away a single tomato, we're discarding the water used for irrigation, the fertilizers, human labor, fossil fuels for transportation, and electricity for refrigeration, the entire resource chain that brought it to our plates. The environmental consequences are alarming. Food decomposing in landfills produces methane, a greenhouse gas 25 times more potent than carbon dioxide. This contributes approximately 8% of all human-caused greenhouse gas emissions globally. To put this into perspective, if food waste were a country, it would rank as the third largest emitter after China and the United States, accelerating climate change at a frightening pace. Economically, the direct cost of food waste exceeds $1 trillion annually worldwide. Food producers lose revenue while paying increasing disposal fees. The average manufacturer spends 4 to 10% of its operating budget on waste management, resources that could fund innovation or employee benefits. Modern food factories face waste challenges due to their operational scale. A juice processing plant might generate 20 tons of fruit pulp in a single shift. Bakeries produce dough scraps, meat processors accumulate bones and trim, and vegetable facilities create peels, seeds, and stems that traditionally went to landfills. Three forces are compelling manufacturers to rethink this approach: rising disposal costs, landfill fees up 30% in the past decade, consumer preference for sustainable brands, 73% of global consumers would change habits to reduce environmental impact, and corporate environmental policies with ambitious waste reduction targets. Companies ignoring waste innovation miss valuable opportunities. Each waste stream contains compounds, nutrients, or energy potential that could be monetized. Coffee grounds contain oils for cosmetics. Citrus peels offer essential oils and pectin. Fortunately, forward-thinking factories have developed sophisticated waste systems. These facilities implement comprehensive capture mechanisms, sorting technologies, and conversion processes that transform waste into value. One beverage manufacturer now extracts compounds from fruit waste for natural food dyes, turning disposal expenses into profit. These transformation systems create new revenue while reducing costs. Some manufacturers have achieved zero waste to landfill status, where every byproduct finds productive use, as new ingredients, animal feed, packaging materials, or energy feedstock. While achieving zero waste looks impressive in corporate sustainability reports, the journey begins by solving a deceptively complex problem: how to efficiently capture, separate, and preserve massive volumes of diverse food materials before they spoil. These collection and categorization systems represent the hidden foundation of the entire food waste revolution, transforming what was once considered garbage into valuable resources. Modern food factories have completely reimagined waste management, abandoning traditional disposal methods in favor of sophisticated collection systems that separate different waste types directly at their source. This fundamental shift allows manufacturers to preserve each waste stream's unique properties and value. Rising disposal costs, consumer demand for sustainable practices, and ambitious corporate environmental targets drive this evolution. In practice, specialized conveyor systems automatically direct different waste materials along separate paths as they emerge from production lines. At food processing facilities, peels, seeds, and pulp follow distinct routes, preventing the cross-contamination that would limit their potential uses. The technology has grown increasingly sophisticated. Optical sorting equipment using artificial intelligence and machine vision categorizes waste based on type, color, and quality, much like recycling facility technology but adapted specifically for organic materials. The precision of the sorting determines whether materials become animal feed, compost, biofuel, or ingredients for new food products. Temperature-controlled collection systems work in concert with these sorting technologies to slow spoilage during transport between production and processing areas. At Nestlé's facility in Japan, vacuum tube systems move waste directly from production lines without human handling, preserving material integrity while reducing contamination risks. This integrated approach has enabled the plant to divert an impressive 99.7% of its food waste from landfills. After collection, advanced analytics determine optimal uses for each waste type. Computer systems analyze protein content, sugar levels, and fiber composition, allowing manufacturers to route materials to their highest value applications. At the Japanese facility, this meant transforming cocoa husks into livestock bedding, coffee grounds into fuel pellets, and fruit remnants into biogas, all guided by real-time analytics determining which application would maximize value. What makes these systems effective is their holistic approach. Rather than treating collection as an isolated step, manufacturers integrate it into a comprehensive system that includes transportation, treatment, and continuous monitoring. Clean, categorized food waste reaches appropriate facilities in optimal condition for its intended reuse. These systems represent a substantial investment for manufacturers, requiring specialized equipment, dedicated factory space, and trained personnel. However, the return on investment can be significant through reduced disposal costs, new revenue streams from selling byproducts, and strengthened brand reputation among sustainability-conscious consumers. Beyond simply sorting and categorizing waste, forward-thinking manufacturers are asking a revolutionary question. What if food waste isn't waste at all, but rather undiscovered ingredients? The beer you enjoyed last weekend created byproducts that might be in the energy bar sitting in the pantry right now. This transformation represents a fundamental shift in how factories view materials previously destined for disposal. Modern food factories are pioneering techniques to extract usable components like nutrients, flavors, and textures from production byproducts. These components become the foundation for entirely new food products that consumers might never suspect originated as waste. The process recognizes the untapped potential in every part of our food. Consider regrain's story. Barley grains soak in hot water, release their sugars for beer, and would typically head to landfills. Instead, these protein-rich grains travel to regrain's facility where they're transformed into nutritious flour for energy bars and chips. What was once discarded now becomes a sought-after ingredient, diverting thousands of tons from landfills annually. The journey from waste to plate presents significant hurdles. Food scientists must overcome technical challenges to ensure these repurposed ingredients meet strict safety standards, removing bitter compounds, ensuring consistent quality, and developing appealing textures while adhering to rigorous manufacturing standards. Fruit juice production showcases another transformation pathway. After apples are pressed for juice, the remaining pulp, rich with fiber and flavor compounds, undergoes specialized processing. This formerly discarded material emerges as fruit leathers, jams, and natural flavor enhancers. Yesterday's juice byproduct becomes today's nutritious snack, creating a closed-loop production system that maximizes every resource. Your morning coffee routine generates grounds that hold hidden potential. As these aromatic remains leave your coffee maker, innovative companies capture them, extracting valuable oils that enhance energy bars and baked goods. The ground's journey from trash bin to treasure creates new revenue streams while reducing coffee's environmental footprint. Kitchen scraps follow a different transformation path. Vegetable peels and trimmings undergo controlled fermentation, developing into rich flavor bases for soups and sauces. These natural enhancers add complexity to products while reducing the need for artificial additives. The humble potato peel becomes the foundation for tomorrow's gourmet soup. The seafood industry transforms fish processing byproducts, scales, bones, and trimmings into valuable ingredients. These materials become gelatin, collagen supplements, and flavor enhancers. What fishermen once discarded now becomes premium supplements that consumers actively seek on health food store shelves. Renewal Mill exemplifies this waste-to-value revolution with Okara, soybean pulp left from making tofu and soy milk. This nutrient-dense material transforms into high-protein flour for cooking and baking mixes found on major grocery store shelves. Their success demonstrates both technical feasibility and growing consumer acceptance of sustainable food options. The environmental benefits are substantial. Materials diverted from landfills reduce methane emissions while creating value from former waste. These innovations collectively challenge our perception of food waste, revealing that what we once considered garbage often contains hidden ingredients waiting to be discovered. Those economic advantages extend beyond just creating new foods. They're revolutionizing packaging in ways that could eliminate plastic waste entirely. The milk protein casein, typically discarded as dairy waste, is now being transformed into water-soluble films that leave no microplastic residue behind. Lactips processes this dairy byproduct to create packaging that completely dissolves without environmental consequences, unlike conventional plastic wrappers most of us have used our entire lives. The packaging revolution in food factories represents an elegant form of waste transformation, using food byproducts to create the materials that protect our next meal. This circular approach addresses two environmental challenges simultaneously: reducing food waste while tackling plastic pollution that threatens our oceans and ecosystems. Natural polymer content found in food waste streams provide the building blocks for flexible, durable, and biodegradable packaging. Protein structures in milk waste, sturdy fibers in vegetable trimmings, and complex carbohydrates in fruit peels contain compounds that can be extracted and reformed into functional packaging materials. In Mexico, Biophase has pioneered a creative solution addressing a unique waste stream. They collected avocado seeds and skins, byproducts from the country's massive guacamole and avocado oil industries, and transformed them into bioplastic food containers. These containers serve the same protective function as conventional plastics, but decompose naturally without persistent pollution. The symmetry is remarkable. The container holding your guacamole could be made from the very avocados used to make it, mimicking how nature's protective layers return to the earth. For delicate items requiring cushioning during transport, Ecovative Design offers an alternative solution to petroleum-based styrofoam. Their process binds agricultural waste with mycelium, the root structure of mushrooms, creating protective packaging with the same shock absorption as conventional materials. This mushroom packaging demonstrates how nature's decomposition mechanisms can create materials that protect foods during shipping before safely returning to the earth. Creating these packaging materials requires sophisticated processing technologies increasingly integrated into food manufacturing facilities. The journey from waste to packaging begins with mechanical grinding, followed by chemical extraction where specific components like cellulose or proteins are isolated. Heat treatment then helps shape and solidify materials, followed by molding processes that form the final products. These production systems represent a fundamental shift in waste management, treating waste as a resource integrated directly into manufacturing. This creates a closed-loop system where outputs from one process become inputs from another, reflecting the waste-free cycles found in natural ecosystems. Italy's Agricola Moderna exemplifies this circular approach by growing microgreens in compostable trays made from previous harvest waste. Customers can compost both unused plant matter and the tray itself, completing a perfect cycle where waste ceases to exist as a concept. Engineers face substantial technical challenges ensuring these materials withstand moisture, provide adequate shelf life, and maintain food safety standards while remaining fully biodegradable. When successful, these innovations deliver a powerful environmental win-win, reducing food waste while eliminating plastic pollution at its source. While packaging innovation transforms waste into protective materials, there's an entirely different kind of alchemy happening in modern food factories, one that extracts microscopic compounds worth their weight in gold. Within the cellular structure of what we consider waste lies a molecular treasure trove that sophisticated technologies can now access, creating entirely new value chains for materials once destined for disposal. This is essentially mining for gold in our waste streams. The financial math is compelling. Some tomato processors generate more revenue from lycopene extracted from discarded tomato skins than from their primary tomato paste products. This invisible economy of molecular extraction revolutionizes how manufacturers view their waste streams, transforming them from cost centers into profit generators. The compounds hidden in food waste, proteins, polyphenols, fiber, and specialized peptides, serve as critical ingredients in premium foods, cosmetics, pharmaceuticals, and industrial products. These compounds function as active ingredients that give products their effectiveness and commanding price points. Consider the humble orange peel. The peel contains limonene, a potent compound giving citrus its characteristic scent. Food processors extract this essential oil before peels move to other uses. The extracted limonene becomes a prized ingredient in cleaning products, fragrances, and flavor enhancers, often worth substantially more per ounce than the original fruit. Coffee processors have discovered similar value. After beans are roasted and brewed, the grounds still contain caffeine and antioxidants. Cosmetic companies acquire these compounds for skincare products that reduce under-eye puffiness and fight visible aging, creating new revenue streams while providing effective natural ingredients for beauty products. Wine production generates millions of tons of grape pomace annually, the skins, stems, and seeds left after pressing. Manufacturers now extract resveratrol and other polyphenols from this material. These compounds appear in nutritional supplements with anti-aging benefits and as natural preservatives that extend shelf life without artificial additives. The extraction technologies themselves represent remarkable innovations grouped into several approaches. Supercritical CO2 extraction uses carbon dioxide pressurized until it behaves both as liquid and gas, selectively pulling specific compounds without harsh chemical solvents. Enzymatic extraction employs natural enzymes to break down cell walls and release targeted compounds, mimicking natural biological processes under controlled conditions. Ultrasonic extraction uses sound waves to create microscopic bubbles that collapse, disrupting cellular structures and releasing valuable molecules without excessive heat. These processes require sophisticated equipment and precise control to isolate pure ingredients, representing substantial investments that often deliver rapid returns due to the high value of extracted materials. The economics of molecular extraction are reshaping manufacturing priorities. Materials once rushed to disposal now receive careful handling to preserve their biochemical potential. Production lines are being redesigned to segregate valuable waste streams, with R&D departments researching new extraction possibilities. Beyond valuable compounds, food factories have discovered a fundamental solution to handling large-scale waste, transforming it into the energy that powers their operations. In an era of rising energy costs and climate concerns, some facilities now generate enough power from materials they once paid to dispose of that they've become completely energy independent. The biological gold mine within organic waste contains chemical energy that can be released through controlled processes to generate electricity, heat, and fuel. Anaerobic digestion stands as the most widely adopted approach, where microorganisms break down organic waste in oxygen-free environments. This biological process transforms food scraps into biogas, primarily methane and carbon dioxide, over several weeks, creating energy directly from waste. This biogas serves multiple purposes. Food factories burn it in generators for electricity, use it as heating fuel, or refine it into renewable natural gas. Some facilities power their delivery trucks with RNG, creating a closed-loop system where yesterday's waste fuels tomorrow's deliveries. The scalability makes this approach particularly attractive. The Des Moines Metropolitan Wastewater Reclamation Authority operates 6 massive 2.7 million-gallon anaerobic digesters, processing over 60 truckloads daily of commercial waste. These generate more than 2.1 million cubic feet of biogas every day, powering their operations while selling excess energy to nearby facilities. Anaerobic digestion yields digestate, a nutrient-rich byproduct that serves as an excellent soil amendment. East Bay Municipal Utility District in Oakland pioneered this approach as the first wastewater treatment plant in America to convert post-consumer food scraps to energy, capturing methane from restaurant waste while composting the remaining materials as natural fertilizer. Alternative technologies complement anaerobic digestion in some facilities. Pyrolysis exposes waste to high temperatures without oxygen, producing bio-oil or fuel and biochar for soil improvement. These systems integrate with factory operations, capturing heat from generators while directing liquid byproducts toward fertilizer production. The economics prove compelling. Gill's Onions exemplifies this transformation. Their $10.8 million waste-to-energy system processes 300,000 pounds of onion waste daily, generating enough electricity to meet 100% of the facility's needs. Annual savings of $700,000 demonstrate how waste management transforms from cost center into profit driver. Academic institutions have embraced this approach too. The University of Wisconsin Oshkosh's dry fermentation anaerobic digester processes campus food waste alongside agricultural plant waste, producing enough energy to power up to 10% of university needs. Major retailers recognize the potential as well. Whole Foods Market has diverted 12,500 tons of food waste to anaerobic digestion facilities since 2014, preventing nearly 9,000 metric tons of CO2 emissions while generating renewable energy for thousands of homes. This integration represents a fundamental shift in how factories view waste, as an untapped resource rather than a disposal problem. By converting materials once destined for landfills into usable energy, manufacturers reduce their environmental footprint while gaining energy independence. The journey from farm to table doesn't have to end with waste. As we've seen throughout this exploration of modern food factories, the industry is rapidly transforming what was once considered garbage into valuable resources through innovative technologies and processes. Your everyday choices matter. When you purchase from companies transparent about waste reduction, you actively support sustainability. At home, embrace meal planning, proper food storage, and creative leftovers use. These small actions create powerful change. You're joining a global movement, reshaping our relationship with food and waste. Together, we're building a circular economy where resources are valued, preserved, and given new life. What sustainable practice will you start today?